let's get started. We'll finish up week number 6. You know, next Monday we were just talking about Monday is the beginning of week number 7. We are coming up on the halfway point going through this semester. The other good news is that we got an exam on Monday. We're covering chapter 3.
Your good news and my good news are 2 different things.
You keep using that word. I think it does not mean what you think it means.
What?
Good news.
I know.
You don't get the reference.
I do.
Okay. Well, let's start off with asking, does anyone have any questions from the homework? Any of the material from chapter 3 that you want to cover? You want to go back and revisit?
Not yet.
Well, I want to cover something that came up in one of the homework assignments. I don't know if y'all have gotten to it yet or not. But I noticed that the book kind of just glossed over this one little tidbit. We've talked about vectors in polar form, where we give a magnitude and a direction as an angle. And we convert that from polar form, written as, to the rectangular coordinates form by writing okay? And I've shown you that in order to add vectors together, you must convert them into rectangular form. Then you can add their components directly. Now, we did not cover this in this chapter at all. But if you want to multiply vectors, you have to put them back in polar form. Okay? Now, that is a true statement for those who, I think all of you are in the electronics programs. So when you start doing vector multiplication, it's going to be in the context of circuit analysis. Okay? Bottom line is, you need to multiply a vector. You're going to put it in polar form, and then you just multiply the magnitudes or divide the magnitudes. And if it's multiplication, you add the angles, and if it's division, you subtract the angles. It doesn't. Don't worry about remembering any of that. That's not going to apply in our, at this point, not at least in this course. We may get to it later. I honestly haven't looked that far ahead, but strictly speaking, when you multiply vectors together, it's no longer just a scalar multiplication issue. It becomes ambiguous as to just exactly what you're doing when you multiply. So they have 2 different kinds of multiplication of vectors. There's a dot product and there's a cross product. And they're 2 different operations. Okay? So the good news, and I think even you will agree with me that when I say this is good news, we don't have to worry about dot products and cross products and all of that, not at this point. But we do have to worry about scaling. Okay? Scaling a vector is simply a matter of multiplying the vector by a scalar value. So if you have a vector m at an angle of theta, and you want to make it 3 times as big, just multiply the magnitude by 3. And no allusion to the manufacturing company. That's how you scale a vector. If you're multiplying it to make it bigger, you just multiply the magnitude and it gets bigger. So what if you've got it in rectangular form? How do you scale it at that point? Well, it came up in one of the homework problems, and it was never really addressed directly in the lecture or in the book that I saw. But let's look at how this would work. If we've got a vector and we've multiplied it by 3, we made it 3 times as big as it was. And then we want to convert it into rectangular coordinates, we would simply multiply 3 times m, the new magnitude, times the cosine of the angle, times the unit vector I, plus 3 times m, times the sine of the angle, times the unit vector j. You see what just happened? Because we were doing a scalar multiplication of the vector, it didn't matter whether it was in polar form or in rectangular coordinate form. We could have gotten the same result if we'd have just said 3 times that and then distribute the product through the parentheses. It becomes 3 times m times cosine theta I plus 3 times m times sine theta j. Same result. So when you're it's one of the homework problems that says to add 3 times a plus 2 times b minus 3 times c or something like that. But it was never made explicit how you scale a vector. Well, it turns out in this case, either way, whether it's in polar or rectangular, you just multiply it by the scalar and it works. You get a legitimate result. So, any questions about this? No? Okay, good enough. That was painless. Now, this came up in the lab yesterday, and it's going to come up on your homework assignment. That's probably going to come up on the exam. But when you're working with vectors, it's important to remember once you've converted it into rectangular coordinates, it's important to remember that which coordinate goes with which axis. Which component goes with which axis. This came up yesterday in lab with where we measured the horizontal velocity component, and then we started calculating the time that it was going to take for a projectile to fall and hit the ground, and started plugging in that horizontal velocity component into the vertical velocity equation. And you got to remember to keep these things straight. It's another example of the same point that I've stressed to you before. Your calculator will not do the math. Your calculator will do whatever arithmetic you type into it, but you have to do the math. You have to keep track of what you're multiplying, what you're dividing, what you're adding, what quadrant is your vector in. This one came up several times in the homework. What quadrant was the vector in? People started looking for converting back into a polar form from the rectangular form, and they would take the y over x, do the inverse tangent, and get minus 13 degrees. But minus 13 degrees puts them in quadrant 4. When the actual vector should have been over in quadrant 2 are 180 degrees opposite that. When that happens, remember to add that 180 degrees. You have to do the math. The calculator just does the arithmetic. I know I'm becoming redundant. I'm saying the same thing over and over again. There's a reason. It's important. And if repeating it over and over again is what it takes to make you remember it, then that's what I'm going to do. The last section of this chapter that we need to cover today is called relative velocities. This is an example they use in the book. Got a guy standing here. This bow and arrow. Got an apple hanging from the tree limb. He wants to shoot this arrow through the apple, but at the exact moment that he fires the arrow, the apple drops and starts to fall. How would he adjust his aim to hit the arrow so that the arrow would hit the apple here instead of up here? Well, the fact is he wouldn't. He would still aim for here. This is what we've already covered, because once he releases the arrow, gravity is going to make the arrow fall at exactly the same rate as the apple. Okay, that's the whole premise behind the projectile motion. And analyzing motion in two separate axes as two independent vectors. What about, okay, here's one that you may have encountered before. You want to swim across a stream. How many of you have ever gone to swim out into the ocean or in the Gulf of Mexico? How many of you have heard of rip currents or undertows? How many of you have been told how do you deal with it if you find yourself being sucked out to sea by one of these rip currents? Huh? Well, okay. It's a good thing you showed up for class today. How would you deal with it? If you were caught in a rip current, an undertow, whatever you want to call it. I know they like to say now a rip tide is not technically what it is, but you understand what I mean when I say that. So how would you deal with it? If you were found yourself caught in a rip current and you were being drug out to sea, what would you do?
Yes, swim sideways.
Swim sideways. What about you? Why?
To meet your mark so that way you're not going out further.
Well, here's a rip current is a very narrow stream, and I don't know how wide they are. They can be 10 feet wide, 50 feet wide. Doesn't matter. The point is, once you're in it, it's pulling you out to sea. If you try to swim back towards the shore, you're swimming against the current. You're going to just keep, and you're not going to outswim it. You're just going to keep running. You're going to use up all your energy as you get sucked further and further out. But if you swim horizontally, parallel to the shore, you're still going to get sucked out as you move, while you're swimming, but you're going to be crossing the stream. So you're actually going to be moving at an angle until you get to the edge of the rip current, at which point you'll be back in normal water and you can then swim to shore without exhausting yourself. So yeah, you're right. Swim sideways is exactly what you should do. The reason is because of what we're calling relative motion. Suppose you've got a river. You're here. You want to swim to here. Easy enough, you swim straight across, right? With some velocity. And then in a certain amount of time, you're going to find yourself on the other side of the river. If you swim with a velocity of 5 meters per second, and I don't know if that's realistic or not, so don't quote me on it, but if you're swimming with 5 meters per second and it's 50 meters across, then it's going to take you 10 seconds to swim across the stream. Right? The point is, in 10 seconds, you will have swum from here to here. But what if the current in the river is also flowing at 5 meters per second sideways? Now, as you start swimming this way, you're also being pushed this way at 5 meters per second. Which means in the time it takes you to swim 50 meters across the shore, across to the opposite shore, you're also being pushed 50 meters downshore. That means your net velocity is the sum of the two relative velocities. Okay? The actual velocity that you move with as you're crossing this river is not the 5 meters per second at 90 degrees. That's the work you're putting into it. You're doing 5 meters per second at 90 degrees. But the water is also moving you at 5 meters per second at 0 degrees. Horizontal. And your net motion, your actual velocity vector, is the vector sum of you plus the water. And how would you calculate that? Convert them into rectangular coordinates, add them together, convert them back into polar coordinates. Oh, that's something else I want to point out to y'all. There have been several occasions in the homework assignment this week where it says, add these two vectors together. And a lot of you did, and then went and converted them. I say a lot of you, some of you at least, added them together, and then went and converted them. Once you added them, converted them back into polar form. And that's fine. I appreciate the wanting to be thorough and be complete. But if the only thing the question asks you for is the sum of the vectors, once you have them in rectangular form, that is a perfectly legitimate form of that vector. That is a perfectly legitimate final answer. Unless it tells you specifically it wants them in polar form or in rectangular form. Whatever form you end up in it's good. It's a final answer. It's a perfectly legitimate representation. Just be careful, because if it says show me, give the answer in both rectangular and polar form, then you need to do both. Okay? Be sure to answer what the question asks for. But it's like, never mind, that's a trick class issue, so I'm moving into it. But in this case, what would the actual velocity of this swimmer be? It would be the magnitude V total is, somebody? Well, the way we set up the problem, do y'all, first of all, do y'all see that the way we set the problem up, it's already in rectangular coordinate form? It's the vector sum of two orthogonal vectors. So you've got V total is actually equal to 5 meters per second I plus 5 meters per second J. Okay? That is the final vector. But if we wanted to express it as a polar form, what would the magnitude be? No, in fact, this was an issue for one or two of you on homework. That actually, I think somebody just got tired and frustrated and didn't feel like finishing the homework. But at the end, it started asking them to add A and B together, and they were just saying, okay, well, 25 at 30 degrees plus 20 at 20 degrees is 50 at 50 degrees. It doesn't work that way. It's just not even close. How do we get this magnitude? Bingo. Square root of 50. That's the magnitude of the vector sum. Now, what is this new angle? How would you calculate the new angle? Well, no, actually, because I set the thing up in already in horizontal coordinates. This is 90 degrees from here to here. This is 0 degrees here. So theta would just be the inverse tangent of y, which is 5, divided by x, which is 5. This y and x, which is the inverse tangent of 1. Where is tangent equal to 1? 45 degrees, pi over 4. Now, I know you're all working in the engineering school, so you would want to type in 50 and hit the square root button and round it off to a number of significant digits. Perfectly acceptable to do that. I would point out to you that mathematically this is the exact value. This is the actual exact answer. So, of course, mathematically doesn't account for the fact that we would have been dealing with measured values and significant digits all along. So I leave it like that because I don't have a calculator in my head and I have no idea what the square root of 50 is. 7 is 49, so it'd be a little over 7. I know 7 is 49 and 8 is 64, so it's going to be real close to 7 point something. Do we need to go back and revisit doing these conversions from rectangular to polar and back? If you're given, let's look at this because I want to make sure y'all are clear on this. you're given vector A is equal to 50 units at an angle of 30 degrees. Vector B is equal to 40 units at an angle of 25 degrees. How do you add those together? It is not as simple as 40 and 50 is 90 and 20, 30 and 25 is 55. That is not right. That won't even earn you a partial point. So, what is the first thing you have to do to add these vectors? Put them in a rectangular form. That's right. You have to write A as 50 cosine theta I, which would be, 50 times cosine of 30 degrees times I plus 50 times the sine of 30 degrees times J. This is 40 times the cosine of 25 degrees I plus 40 times the sine of 25 degrees J. Now you can just add it. 50 plus 40 is 90. Oh, actually, when you do this, you're going to want to do the trig first, but you'd have to actually do the trig and turn those into numbers. So let's do that. Cosine of 30 is 0.866. So this becomes 43 I plus 30, sine of 30 is 0.5. So that's plus 25J. Cosine 25 is 0.906 times 40 is 36. I plus sine of 25 times 40 is 17. J. Now you can add them. 25 plus 17, 42 times J, 43 and 36, 79 I. That is A plus B. And if all they ask for is the vector sum, they're done. But how would we turn that back into polar coordinates? Same thing we did over here. This is just, if we look at this graphically, this is just 79 along the x-axis plus 42 along the y-axis, positive direction in both cases. That means this is the vector sum. This is the magnitude of their sum. And there you got your right angle, Pythagorean's theorem. This squared plus this squared equals that squared. So, the magnitude of A plus B is equal to the square root of 79 squared plus 42 squared equals let's take it one step at a time. What are we dividing? What are we taking the inverse tangent of? Y over X. 42 divided by 79. And that gives us 28 degrees. You can see how we would have ended up with a completely different angle if we just added the two angles together. There's your vector sum. Did we talk about how this inverse tangent thing works? Did I explain to y'all why you have to be very careful when you start doing this? You have to do the math. You can't just trust your calculator to do it for you. Say again? No, not necessarily. I want y'all to understand what's going on here. So let's look at this. We plot a graph of tangent. What is tangent of 0? Okay, a little trig refresher for you. Tangent of theta, by definition, is equal to the sine of theta divided by the cosine of theta. Okay? Remember your unit circle. At 0, at an angle of 0, cosine is 1, and your sine, your y-coordinate, on the unit circle, the sine of theta is equal to the y-coordinate of that point on that circle, and the cosine is equal to the x-coordinate. So if you have this point, x, y, where r is equal to 1, then the sine of theta is equal to y, and the cosine of theta is equal to x. Do all of this, any of this refreshing anybody's memory? No? Well, I'm not going to go back and teach a trig and prove it to you, but just trust me, take my word for it. If you're dealing with the unit circle, if you're dealing with any circle, then it would just be r times sine of cosine. Sine of theta would give you the radius times the sine of the angle will give you the y-coordinate at the end of that vector. The radius times the cosine of the angle will give you the x-coordinate at the end of that vector. So, at tangent of 0, sine at 0 is 0. So the tangent of 0 is equal to 0. So this is the first point on your graph of the tangent. You go out to 45 degrees. What do you get? Somebody put in 45 degrees and press tangent. It should give you a 1, correct? Okay, at 45 degrees, your tangent value is 1. Somebody put in minus 45 degrees. Negative 1. So here's our tangent function so far. Let's go on out to 90 degrees. Somebody put in 90 degrees, hit the tangent button. What does it give you? Error or undefined. Why? What's happening there? These are what are called, in mathematics, these are called asymptotes. They're points on the x-axis that tangent can get arbitrarily close to, but can never equal. Do you see why? What happens when you come around to 90 degrees? What's the x-coordinate? It's 0. Here, you're at a point 0 and 1 on the unit circle, or 0 and r on some other radius of circle. What happens when you divide by 0? You get an error. It's undefined. Did I not show y'all the thing about why division by 0 is undefined? Did I show y'all the proof that 2 is equal to 1? Did I? I didn't. Point is, when you divide by 0, it becomes undefined. The closer you get to 0, the closer you get to 90 degrees, the closer tangent gets to infinity. Somebody put in 89.999 and hit tangent. What do you get? $57,295. Somebody else put in 89 and then 4 nines. 0.9999. Now, the closer you get to 90, the higher and higher this gets. And it does this. Same thing happens over here. The closer you get to minus 90, the closer it gets to negative infinity. And then it repeats. Over and over and over again. Infinite number of times in both directions. So, when you punch in, now we're going to go back and revisit a little bit of algebra. What's the definition of a function? A function, tangent is definitely a function. That means that for every value of x you put in, it will give you one and only one value of y. Okay? Any x. Pick an x, any x, it will give you one and only one value of y. But, if you look for one value of y, you can have an infinite number of potential x's. You have one here, you got one here, you got one here, and spread out by 90 degrees up and down the line, infinitely in both directions. One y, one tangent value, can give you an infinite number of solutions, x values that will produce that value of y. So, what happens when you add two vectors together and you end up here at, say, 100 degrees? Somebody put in 100 degrees and hit tangent. That would be about right here. Say again. You got negative. Well, look here, minus. Oh, you went to I'm sorry, you're right. I said 100 degrees. That would be here, not there. So you put in 100 degrees, and you get minus 5 point something. Right? Now, with that number, that minus 5 point something, you've got everybody do this. Type in 100, hit tangent. Get that minus 5 point something something on your display. Now, hit inverse tangent. It's going to give you what? Minus 80 degrees. Why is that? This is the way your calculator works. And again, I'm hitting on this same point again because it's important. You cannot let your calculator do the math for you. You have to do the math. When you give it a number and say, give me the inverse tangent, it's going to give you a result from here to here, from minus 90 to plus 90 degrees. If your vector is not in that range of minus 90 to plus 90, but it's somewhere else, you need to know where it's going to be. Looking in terms of the unit circle, or of any circle of just the 4 quadrants, here is 0, here is plus 90 degrees, here is minus 90 degrees. When you do a tangent, when you take a tangent value and ask for you do y divided by x and ask for the inverse tangent, it's going to give you something from here to here. And if you happen to be right here, it's going to give you this one here. If you're over here in quadrant 3, and you take the inverse tangent, it's going to put you here in quadrant 1. This is the way the algorithm works. The algorithm only solves for this first principal period. The same thing will be true of cosine and sine. There is a principal period that it will work out of, and that's where the algorithm will give you an answer from. You have to know, out of all of those infinite number of x values, which x value is the one you're looking for. Now, in this case, you want to find this angle. You know that your vector is here in quadrant 2. You take the inverse tangent, and it gives you an answer down here in quadrant 4. How do you get your correct answer? Just add 180 degrees. And that'll put you at the actual angle that you're looking for. But again, you have to do the math. You can't trust the calculator to do it for you. That said, you do need to start thinking in terms of the standard angle position. And I know that this isn't always, you can't always do this because the way they write the problems in this book, sometimes they go with like the vector is 23 degrees, one of them in particular said the vector is 23 degrees above the horizontal, the negative x-axis. And that's how they describe the vector. Well, what's the standard angle for that vector? What's 180 minus 23? What, 57? Or 157? Don't quote me on that. It's too early in the morning for me to do arithmetic. So if you're working with this in polar form, you can plug in that 157, and now when you do sine and cosine, it's going to give you the proper sign. If you're just using, what if you were doing this vector? What if you were working this problem? Say, let's say this is a 20 at an angle of 23 degrees above the horizontal, the negative x-axis. What did I say? 20. How would you write that in rectangular coordinates? Twenty times cosine of 23 degrees. I, okay. That would give you this vector here. Okay, so you could certainly do that, and that would tell you this length. But again, you have to do the math. It's pointing to the left. That means it's a minus x coordinate, not a plus. You take the sine of 23 degrees, and it's still going to give you the positive coordinate. But if it were 23 degrees below the negative x-axis, then you would also have to change the sign of your y component vector as well. Okay? If you put it in standard form to begin with, 157 degrees, then instead of writing it as 20 and 23 degrees above the negative x-axis, if you just write it as 20 at 157 degrees, now when you punch in 20 times cosine of 157, it's going to give you a negative number. And it is crucially important when you start adding vectors together. It is crucially important that you keep track of the proper sign of each one of those vector components. Because if you add a negative number, you're subtracting. You're looking for the difference between those two vectors. If you subtract the negative number, you're adding. All those arithmetic rules apply as long as you keep the signs of each one of the components straight. Does anyone have any questions? Does anyone want to ask any questions about other material from this chapter? Get ready for our exam on Monday. This one, chapter 3. Vectors, and in particular as they apply to projectile motion in 2 dimensions. Once you take a vector, you convert it to rectangular, you add, subtract, solve the kinematic equations, solve the quadratic formula, define time. I want to encourage you to go back and find that table. Yeah, except this one is on page 60, table 3-1. And it gives you those same kinematic equations broken down into x and y components for use with projectile motion in 2 dimensions. Again, I want to give you just what is the fundamental condition that must be true in order for these kinematic equations to work? Constant acceleration. On the surface of Earth, we meet that requirement because gravity is a constant acceleration, independent of mass. Everything gets accelerated the same amount, straight down, minus g. But again, it's important to keep the signs correct. When y'all are doing these problems, I've seen this come up too. Let me give you a little tip here. And it's probably one that you've all heard ad nauseum. So I'm just going to make you a little sicker and a little more annoyed to have to hear it all over again. But it's important. When you're solving one of these problems, draw a picture. Car drives off a cliff with Thelma and Louise in it, into the Grand Canyon. It leaves the cliff with an initial velocity of, I don't know, 58 miles per hour or whatever. Once it leaves that cliff, what is its acceleration? It's minus 9.8 meters per second squared. Straight down. Does it have any horizontal acceleration once it leaves the cliff? No, the back wheels can spin in the air all they want. It ain't going to push the car no further. Not an airplane propeller. No more acceleration. Put an airplane propeller on it. Now these kinematic equations don't work anymore because now you have thrust. So if it has any horizontal acceleration, that acceleration has to be constant. Keep your signs correct, straight. So the general rule, you're going to want to set y equals 0 at the ground. And start off at some positive value of y. Because now your negative acceleration is going to push you further down to a lower y value. If you set this equals y equals 0, this becomes y equals some negative number. But when you accelerate negatively, it means you're now expecting the car to be pushed up instead of down. Actually, if you set this equal to that would be true if you set this equal to positive. You could set this equal to 0 and this to negative y, and it would work because now negative is still going down. But if you set this equal to 0 and this to a positive y value, negative acceleration would be pushing you up. So draw the picture. Make sure everything makes sense. Then start doing the arithmetic. First, do the math. Then do the arithmetic. Once you've drawn it out, and you know, okay, I know that I'm going to add these vectors, I'm going to end up over here in quadrant 2. So you know that when you take the inverse tangent at the result and find the angle, it's going to be 180 degrees up. Add it in. Do the math, not just the arithmetic. Have I repeated that enough that y'all are going to remember it yet? Okay. You know where my office is if y'all come up with any questions before Monday? And if I'm not in my office, wait until tomorrow. You can try sending me email. I may see it, I may not.
He goes nothing. Shit.
sign in? Did you sign in? Darnell.
Sir.
It's one more name that I now associate with his face. You know why I remembered your name to begin with? Darnell in Yale County. True grit.
Get out!